Welcome back. We are in the second segment of Lecture 7 on Introduction to Regression. And the goal in this lecture is just to get the basics of regression and now to sort of revisit the concept or the logic behind null hypothesis significance testing. I introduced NHST in sort of bare bones fashion when we talked about correlation and the assessment of reliability in correlation. But now I'd like to take a finer look at NHST and uncover some of the most common problems and criticisms that people have leveraged at NHST. In particular, we'll go through the logic again. I'll highlight 3 really critical problems with this approach, and then I'll suggest some remedies. And this will become really important as we go into R in Lecture 9, and we start to look at the significance of regression coefficients and correlation coefficients. So we can look at the R output and we'll get p-values that tell us whether a regression coefficient is statistically significant or not. And we need to have this sort of general discussion now about NHST to fully appreciate what statistically significant really means. So that's the goal of this segment. So remember from our discussion about correlations, I went through the basic logic of NHST, and the way this works, and I sometimes refer to it as a game, because it is a little bit of a game, is before we conduct an experiment or do a study, we assume that the null hypothesis is true, and the null hypothesis just says that there's no effect. So in the context of correlation and regression, you would say, well, I'm just going to assume that the correlation between x and y is 0. And that's a sort of odd assumption, so you should be already starting to question, why are we playing this game? And that's a good question to have in your head. And there are a lot of scientists out there, especially in social sciences, especially in psychology, who would say that we shouldn't be playing this game. But it is still the most common approach to hypothesis testing, so it's important to understand it as we move forward. So then, of course, the alternative hypothesis is that the correlation is not 0. Here I've presented it in what's called a directional test. So I've said the alternative is that the correlation is greater than 0 or positive. I could have said it's just not equal to 0. So that's non-directional. Either way, it's up to you. Now that we're in regression, I want to present this with respect to the unstandardized regression coefficient, b, in the regression equation. So the null hypothesis is that the slope relating x to y is 0. And then again, here I presented it in directional fashion, saying that the slope is positive. It's greater than 0. Again, the way this works is we assume that the null is true. Then we calculate the probability of a particular outcome. So say we observe a correlation of like 0.7, which was the correlation between on-base percentage and runs scored. What's the probability of that happening if the true correlation was 0? Well, that seems unlikely, right? So we would get a very small p-value, a probability value. And then we would say, well, that assumption I made must have been wrong. There must actually be a relationship between x and y. That's the logic, but there are some problems. The most important part of this slide is this piece here. Please understand, and I tell my students this at Princeton, if you walk away from my class knowing just one thing, please remember this, that the p-value that you see reported in research articles or when people say it's statistically significant, please remember what that p-value really means. It's really a conditional probability. It's the probability of obtaining this outcome or these data. So that's the probability of D is the probability of obtaining this outcome, these data, given, that's that vertical bar, you can read that as given, the assumption that the null hypothesis is true. So that's a mouthful, but let's say it again. What the p-value really means is it's the probability of obtaining this outcome given the assumption that the null is true. Okay? That's critical to understand as you think about this idea of statistically significant and as you look at p-values in your R analyses. So again, if we play this game, NHST, the NHST game, then you'll wind up in one of these four outcomes. So as the experimenter, you have to decide to reject the null hypothesis or retain the null hypothesis. And in the world, and the truth is out there, or the truthiness is out there, since this is all probabilistic. Either the null is true or the null is false. We don't know. That's the point why we're engaging in the research in the first place, right? So you can think of these two rows in this diagram. Think of those as sort of alternate universes. You can't live in both of them. Either one is your universe or the other is your universe. Either you live in a world where the null is true or you live in a world where the null is false. And you have to figure out, as the experimenter, which one of these are you in. So as the experimenter, you'll make a decision to reject the null hypothesis or retain the null hypothesis. Of course, if you retain and the null is in fact true, then great, you've made the correct decision. If you reject the null and the null is false, then you've made the correct decision. But you always run the risk of making an error when you play this game. You could reject the null when you shouldn't have. That gives you a type 1 error or false alarm. So it's a false alarm because you're sort of claiming something happened when in fact it really was just a fluke. It's really not an effect. So that's why it's called false alarm. That's a type 1 error in NHST. The other is you missed an effect. The effect really exists, but you fail to detect it, and you retain the null hypothesis. Those errors are always a possibility when you play this game. Now, based on what we know about the normal distribution, and we're assuming this normal distribution, we can estimate the probability with which you will make one of these errors. So again, each of these rows is sort of an alternate universe. So if we just look at the top row, we know the probability of a type 1 error, and as experimenters, we set that value. So we refer to that as alpha, and the most common level for alpha in the social sciences is 0.05. And you may have heard of this before. If p is less than 0.05, then you reject the null and you have statistically significant results. That's where that comes from. And we've all sort of agreed on 0.05 because it's a nice low probability. So only 5% of the time should we wind up with these false alarms. That means that this probability here is 0.95 because this is one universe, that top row. The bottom row is more difficult, and we'll estimate those probabilities based on power. And we'll get to power in lecture 9 when we do some of these examples in R. For now, power is simply the probability that you will reject the null hypothesis when in fact you should. So power is a good thing, statistical power. It's your probability of rejecting the null when in fact you should. And then the probability of a type 2 error is just 1 minus power. And this is a slightly confusing notation. Forgive me. Alpha is the probability of type 1 error. Beta is the probability of type 2 error. That is no relation to the beta, which is the standardized regression coefficient. Just coincidence that beta is used for both of those. Okay, again, we use that normal distribution to estimate those probabilities. So again, the p-value that you see reported and the p-value that you see in your R output is the probability of this outcome given the assumption that the null is true. And you can't do a reverse inference here. You can't say that it's the probability of the data given the null is equal to the probability of the null given the data. Those are not equivalent. So that's a logical error that a lot of people make and a lot of students make. Actually, even some graduate students and even some PhDs still make that mistake. And that's one of the criticisms that's often leveraged at NHST is people are confused about what the p-value actually means. So just don't make that mistake. Again, it's one of the things that I just try to drill into my students at Princeton is don't make that mistake. It's the probability of the data given the null hypothesis. Okay. So as I said, we could apply this NHST to correlations, but what we want to do here is apply it to the regression coefficient, and particularly the unstandardized regression coefficient. So we'll see this more clearly when we do examples in R, but for now, what you'll see is we can calculate a t statistic based on the unstandardized regression coefficient, b, and the standard error of that coefficient. So I showed you in the last segment how you could calculate b by hand. Of course, we won't do that. We'll just do it in R. And how do we get the standard error, and what is standard error? Well, remember when we talked about sampling that if I do an experiment over and over and over again, if I get repeated samples, the statistics I get from each sample will fluctuate somewhat, right? So the mean for one group won't be exactly the same as the mean for the next group. We talked about this in the context of the wine experts, right, with the wine ratings. So if I got a sample of 30 wine experts and I had them rate one of the wines, I might get an average of like 5.5 on a scale of 1 to 10. But then if I got a sample of a different 30, then I might not get 5.5 exactly, I might get 5.6. There's always a little fluctuation from sample to sample, right? That's sampling error. And how much sampling error we expect on average is standard error. And we can calculate standard error for any statistic, not just the mean. We can calculate it for a slope of a regression line. So I could calculate the standard error for the regression coefficient b. And the formula for that is presented here. We'll get into this a little bit more detail when we do the analyses in R, but for now, it's the square root of the sum to squares residual over n minus 2. Why n minus 2? Well, because there are other things that we're estimating in the regression equation. That is the regression constant and the slope of the first predictor. So we have to subtract out those other things that we're estimating. This is a way we'll get a t-value, and if that t-value is really extreme, either really high or really low, then we'll be out in the extreme ranges of this normal distribution. If we're assuming this normal distribution and we're assuming that the correlation or the regression coefficient 0, then if I sampled over and over again, I should get regression coefficients that are all around 0. And that would translate into t-values that are around 0. But if I get a regression coefficient that's really strongly positive, I would get a really high t-value. I'd be way out here. The probability of landing way out there, given the assumption that the null is true, is really low. That's where we're going to get this p less than 0.05 reject the null hypothesis idea. Now I want to move into some of the problems with this approach. And you may already know about some of these. Hopefully to some of you this is review, or you may have just started to spot them as I've been talking about this. And I'm going to talk about just 3 primary problems. There's entire literature on this in statistics. Here we're sort of doing this as applied statistics for behavioral sciences like psychology. So I'm just going to focus on 3 of the primary critiques leveraged at NHST. One is it's said to be biased by n. That is, it's biased by the sample size. And I'll show you why that's true in a second. The second problem is it only allows for a binary outcome. We have to make a decision to either reject or retain. It's very rigid. We may want to say, well, it's not clear if I should reject or retain. There may be a gray area, and you may want to say that to your audience, but technically speaking, NHST forces you to make a decision to reject or retain, significant or not. And third is the null model is a pretty weak hypothesis. It's just saying nothing happens. So if your research is claiming that you found something versus nothing, that's not a very strong argument. Let me just walk through each of these. So what does it mean to say that NHST is biased by sample size? Well, remember that the p-value that we get, as I just showed you from the normal distribution, the p-value is directly a function of the t-value. And t, we just saw, the formula is the regression coefficient over standard error. But again, what's standard error? Standard error is the sum of the squares residual divided by n minus 2. Now, just work backwards through those equations for a moment. And imagine that n gets really, really large. As n gets really, really large, standard error is going to get really, really low, right? Because this is in the denominator. So if this gets really, really large, then standard error gets really, really low. If standard error gets really, really low, then t gets really, really large. And that puts you out in the extremes of the t distribution, or that z distribution. Then you're going to get a low p-value just because you had big N, not because you had a strong regression coefficient, just because you had a large sample. So just by getting a large sample, you can get small effects to be significant. That's what it means to say that this whole process is biased by N. The second problem I mentioned is the idea of a binary outcome. And again, technically speaking, if you're playing this game, null hypothesis significance testing by the rules, you have to reject or retain. There's no middle ground. But what if your p-value is 0.06 and you said alpha is 0.05? You're so close. And what normally happens in that case in real research is we use this phrase that really is meaningless, but everyone uses it. We say, it was marginally significant. That doesn't mean anything technically in null hypothesis significance testing. It's either significant or it's not significant. It can't be marginally significant. So if p is 0.06, technically you should retain the null and you can't claim a significant result. But because we put so much effort into our research and we came close, we say, it was marginally significant. Editor of the journal, please publish my paper. But that's an odd outcome. So there's ways around that. But technically speaking, if you're playing this game, you need to reject or retain based on alpha, which we set, say, at 0.05. The third problem is, and just the third problem I'm mentioning here, there are other problems as well, that this null hypothesis is not a very competitive hypothesis, so to speak, right? You're comparing your research hypothesis to nothing happening. So if all you've demonstrated in your research is that your theory predicts something, and that's better than predicting nothing, that's not a very compelling story. So a better approach would be to have multiple models, multiple regression models, and test them against each other rather than one model versus the null. So that leads me to the three alternatives. And I'm just going to mention these here, and we'll talk about them again in multiple regression in lecture 8, and then you'll see them in action in R in lecture 9. But for now, we'll just talk about what they are and how they provide a remedy or a complete alternative to NHST. So some people would argue, let's not even engage in NHST, let's just do these. And these are effect size, confidence intervals, and model comparison. So effect size allows you to get away from this binary outcome problem, that is reject or retain. Reject or retain, significant, not significant, tells you just did something happen or not happen. What effect size tells you is what was the magnitude of the effect. And you've already seen that starting with correlation, right? So correlations can go from anywhere from, on the positive side, from 0 to +1, on the negative, from 0 to -1. So the closer you get to +1, the closer you get to -1, the stronger the correlation. Right? When we were talking about correlations, at least at the outset, we weren't worried about whether they were significant or not significant. Right? We just looked at the magnitude of them. And that's what effect size means. It's just what's the magnitude of the effect? How strong is the relationship? So you could just look at the regression coefficient, or you could just look at the correlation coefficient. You should look at the standardized regression coefficient, or in lecture 8, the model R-squared. Another way around the problems of null hypothesis significance testing is to look at confidence intervals. And these are highly recommended by hardcore statisticians. So if you're taking statistics from sort of a math guy, and I'm a psychologist first, then sort of a statistician. I wasn't trained in statistics per se. If you were taking this from a math perspective, hardcore statisticians really argue for the use of these confidence intervals. And what do I mean by confidence intervals? Well, remember, every sample statistic is just a point estimate. That is, again, the mean for one sample is only the mean for that particular sample. There's sampling error. So it's a point estimate, meaning it only represents that sample. It doesn't represent the range of means I could get if I get multiple samples. And that's true of any sample statistic. So a mean, a correlation, a regression coefficient. So instead of reporting just the point estimate, what is the mean, what is the correlation, what is the regression coefficient, why not report an interval and say, well, I'm, say, 95% confident that the correlation will fall somewhere between 0.6 and 0.8, rather than just saying, it's 0.7. The way to get to that confidence interval, and we'll see this as we do the analyses in R, is you just take your point estimate and then you add some value based on sampling error and standard error. So again, if in our example relating on base percentage to runs, in that sample the correlation was 0.7, but that's just a point estimate for that sample. The true interval might be like 0.6 to 0.8. Again, statisticians really like confidence intervals. The people who actually engage in applied statistics, like psychologists or sociologists, anybody in the behavioral natural sciences, we tend not to like them because they're embarrassingly large, is a quote from Cohen, 1994, a sort of famous paper on this topic. It's embarrassing to say, well, I think the correlation is 0.7, but then if you say, what if your confidence intervals, it's 0.5 to 0.9, then you've got a really big range. So And that's true often when we have small samples and big sampling error. And we'll see that in action in R. So what I'm saying here is just you can report interval estimates, and they're a function of standard error. And finally, the third problem is that comparing your own research to nothing is not a compelling argument. So a better approach is to do research where two models are competing against one another. Model A makes a certain prediction, model B makes another prediction, and then you can compare the two models. We'll do a little bit of that this week in multiple regression, but we'll come back to that in more detail in the final week of this course. The last lecture will be all about how to do model comparisons. So to wrap up this segment, null hypothesis significance testing is a very popular and very common approach to determining statistical significance, not just in regression, but as we move forward in doing t-tests and doing ANOVAs and doing all sorts of different statistical analyses. So it's important to learn the process, the logic underlying NHST, but it's also really important to understand what the main problems are and why there's so many criticisms of using this approach in the social sciences. So I just highlighted 3 of the problems here, and I suggested a few remedies or alternatives to those problems. And what we'll see in the next lecture when we do multiple regression, and the lecture after that when we do all of this in R, is we'll see how we can do null hypothesis significance testing to see if things are statistically significant, but also to supplement that statement about significance with estimates of effect size, with confidence intervals, and by comparing multiple models.